Have you ever wondered why sand at the beach can feel like you're walking on hot coals, but the ocean water stays so refreshingly cool? I mean, they're both under the exact same sun, so what gives? Well, we're about to find out as we dive into the really cool physics of heat and materials. Let's get right into it. Right? It's a classic summer problem. The sun's just beating down, and you're doing that little high step dance across the scorching hot sand, just trying to get to the water. Now, both the sand and the water are getting the exact same amount of energy from the sun. So, why is there such a huge difference in temperature? Well, the answer comes down to a key property of all materials. And the secret is something called specific heat capacity. Now, I know it sounds super technical, but the idea is actually pretty simple. It's just the amount of heat energy a material needs to soak up before its temperature goes up. You can kind of think of it like this. Some materials are just really stubborn about changing temperature. They have a high thermal inertia and need a ton of energy to heat up. Others, they change temperature much more easily. Okay, now take a look at these numbers with me. Water has a specific heat capacity of over 4,000. Iron, just 412. That means you have to pump almost 10 times more energy into water to get it to heat up by the same amount as a piece of iron. And that's exactly why the ocean can absorb the sun's rays all day long and stay relatively cool, while the sand, which has a really low specific heat capacity, basically turns into a frying pan. And you've totally experienced this in your own kitchen every time you've waited for a kettle to boil. You are pumping a massive amount of energy into that water, all because its specific heat capacity is so high. Now, this property makes water fantastic for things like cooling your car's engine. But yeah, it also means you gotta be patient when you're waiting for that morning cup of coffee. So it seems pretty straightforward, right? More heat equals a higher temperature. But what if I told you that you can keep adding heat to something and its temperature won't move at all? Sounds kind of impossible, doesn't it? Well, let's take a look at this really fascinating exception to the rule. Check out this graph. On the left, we're adding energy to ice, and you can see its temperature is climbing steadily. But then it hits 0 degrees Celsius and something weird happens. The temperature just flatlines. We're still pumping in heat, but the thermometer isn't budging. And look, the same thing happens again at 100 degrees Celsius when the water starts to boil. So where is all that energy going? It's being used for something called latent heat. Think of it as hidden energy. Instead of making the water molecules jiggle around faster, which is really what temperature is, this energy is being used to literally break the bonds that hold the molecules together. It's the energy of transformation, turning solid ice into liquid water or turning liquid water into steam. And you've definitely felt this in action. When you get out of a swimming pool, right? The water on your skin starts to evaporate. To do that, it needs energy, and it literally steals that energy from your own body heat. That's why you feel a sudden chill. It's like your own personal, all-natural air conditioner at work. So we've seen how heat can completely change the state of materials, but it can also affect their strength and how they respond to forces. And understanding this is absolutely crucial for engineers who are designing everything from massive bridges to airplanes. You know, when you apply force to something, it can deform or change shape in two main ways. Elastic deformation is like stretching a rubber band. As soon as you let go, it bounces right back to its original shape. But if you bend a paperclip, it stays bent. That's plastic deformation. It's a permanent change. For an engineer, the difference between elastic and plastic deformation is, and I'm not exaggerating, the difference between a safe bridge and a total disaster. You want the bridge to be able to flex elastically under the weight of cars and trucks, but you absolutely never want it to permanently bend or, even worse, break. Understanding these limits is literally what keeps our structure standing and keeps us safe. All right, the theory is great and all, but let's actually get our hands dirty with some numbers. We're going to solve a classic physics problem to see exactly how you can figure out the specific heat capacity of pretty much any material. Okay, so this is called the method of mixtures. The principle behind it is super simple. Energy can't just be created or destroyed, it has to go somewhere. So if you drop a hot piece of metal into cool water, the heat the metal loses has to be gained by the water. We can set up an equation where heat lost by the metal equals heat gained by the water. And since we know all the numbers for water, we can solve for the one thing we don't know, the specific heat capacity of the metal. Pretty clever, right? So you've taken in a lot of information today. Now it's time to put that new knowledge to the test with a quick little quiz. You ready? Okay, first one up. What's that key formula we use for calculating the heat energy needed to change a substance's temperature? Go on, take a second to think about it. And the answer is Q equals mc delta T. That's heat energy equals mass times specific heat capacity times the change in temperature. That one's a real cornerstone of thermodynamics. All right, next question. This one's a little more conceptual. Why does a pot of boiling water stay at exactly 100 degrees Celsius no matter how high you crank up the heat on the stove? It's because all that extra energy you're adding is being used as latent heat. It's working to break the bonds between the water molecules to turn the liquid into steam. Once all the water has finally boiled away, then the temperature of that steam can start to rise. And for our final thought today, a little design challenge for you. What would make the perfect reusable coffee cup? Hmm? You'd want a material with a low specific heat capacity so it doesn't steal all your coffee's warmth right away. But you'd also want it to be a good insulator to keep it hot for longer. And of course, it needs to be strong enough to not break during your morning commute. What kind of material would you choose? It's questions just like this one that show how all the physics we've talked about today really does shape the world all around us. Thanks for tuning in.